Good morning, everyone, and welcome to this session on accelerating neural networks with customized RISC-V cores. My name's Jon Taylor, and I lead the application engineering team at Codasip. I'm going to talk you today briefly through how we've done a proof of concept using our L31 embedded core and accelerated the MNIST image recognition algorithm using a couple of simple instructions to achieve a very significant performance improvement, and talk about why you might be interested in that and how our technology helps you do that. To introduce Codasip, we were founded in 2014, so we've been around for a little while. We were the first commercial vendor of a RISC-V IP core. We're now 150 people, growing very rapidly, primarily across Europe. All of our R&D is in Europe, and we have sales and commercial offices around the world. When we think about edge acceleration, machine learning on the edge, why we might worry about that, there are a few key benefits to being able to process on small embedded devices rather than work with servers remotely. The first is around autonomy, and that gives you benefits in terms of you're not having to transfer data, saves you both cost of the data transfer and the energy that you're not running wireless of some sort. It's more secure, the data never leaves the device. It gives you the ability to do a modular design with different customizations at different parts of the design you need, and actually not transferring data to and from a remote server can significantly reduce latency as well. But it's not without its challenges of processing on the edge. So first of all, you need the software frameworks, and a lot of these are optimized for larger systems. There are now some MCU-centric frameworks like TensorFlow, like Micro, and that's what we're using in our presentation today. You need lots and lots of data for training data sets and things, and I'm not going to touch on that. We're using an off-the-shelf algorithm. The focus here is on the ability to accelerate rather than the algorithm itself. And obviously you do need compute power to do the processing, and again, many off-the-shelf MCUs have limited memory, a limited instruction set, and might not have DSP capabilities either, and I'll show you how we can address that with Studio. So if we think about the task of image recognition, this is the MNIST algorithm, which some of you may already be familiar with. You have a small input image, it's recognizing numbers in handwriting. You perform a variety of machine learning operations on it, and you get out of it a number from 0 to 9. So if you're going to think about accelerating this, you need to understand what the software is doing, you need to run some profiling, and our Studio tool can help you with that. So you can run your software, you can profile it at a fairly high level and get some strong indications about where the hotspots are, where you might benefit from acceleration. And that can be annotated into the code. So we can see here we've got a couple of particular hotspots, and these relate to the convolution functions that the algorithm is performing. So that starts to indicate the sorts of functions that might benefit most from acceleration. And in particular, we've got a sort of multiply accumulate type operation going on here that takes a significant amount of time. So if we can find a way to accelerate image convolution, we should be able to get a major improvement in performance. If we look at what convolution is actually doing, it's essentially matrix multiply. You iterate over your image, you have values in the image that you're going to operate on, you have a set of weights, and by performing some maths, you can complete your convolution. Using the base RISC-V instruction set, a 2x2 convolution, as we see here, has 4 loads, 4 multiplies, 3 adds, and you might find there are some pipeline stalls due to data dependencies or the load stalling. And as you scale that window size, so as you go up to 3x3 or bigger, and you scale the number of channels, this obviously gets exponentially more complex. So one of the first things we can look at is actually pipelining the loads using a FIFO structure, and it'll become a little bit more clear on the next slide what I mean. But by having a custom data storage element outside of the main register file, we can make all of those pixels available in a single cycle, and we can then extend the ALU to have a big parallel multiplier that will make the maths much, much faster. So we can see that expanded a little bit here. Now, again, if you're accessing in memory, typically as you go along a cache line, your accesses are fast. As you go down successive addresses, those tend to be slower. So if we build a FIFO structure that spans enough that we capture all of the elements for a given matrix, that gives us our ability to do single cycle access. And you can see the FIFO structure here. We push each cycle, we push a new element on, the old one will pop off. And we can use all of those with the weights. The weights might be stored in dedicated registers, either in the standard register file, or you create some custom registers. And all of this can be done within our Studio tool, and I'm going to show you how in a second, but this gives you the ability to do all of that convolution in a single cycle. So Codasip's unique proposition is our Codal processor description language. It's an architecture description language and not a generic HDL, so you can very quickly describe all of the elements you use to build processors. The focus is on increasing efficiency around things like instruction decoders, architectural elements like register files, and we have two levels of modeling. So we model at the instruction accurate level, kind of programmer's view, and that's used to both generate an instruction accurate simulator and to generate your SDK and toolchain, so you get a full C++ compiler based on LLVM, you get debugger, you get simulator and so on. And then on the implementation side, you have a microarchitectural description that includes all of your pipeline, and that's where you can do everything you can typically do in an RTL, so things like worrying about forwarding, data hazarding, all the other fine-grained control you need if you're building a processor. And there's an example here of how you would describe a multiply-accumulate operation in our Codal language. It's very easy to bring in the registers you want to need. If you need a multi-port register file, it's very simple to extend the register file in the architecture description. We then have some assembly encoding that helps you both if you're handwriting assembly or for the disassembly tool. You have binary encoding of the instruction, which again the compiler needs obviously. And then because this is the instruction accurate model, we have a very high level functional description. Now, in terms of using this, I talked about the compiler using it. For simple instructions, the compiler can target these automatically. So you don't need to change your code, you can just recompile it with the new compiler and it will pick up these custom instructions. For more complex instructions, like we have in the case of this convolution operation, you may need to use inline assembly or intrinsics, and again, we will generate the intrinsics for you, and I'll show that being used in a couple of slides' time. So if we take that more complex example of doing that 2x2 convolution, the right-hand side here is what it looks like in Codal. And again, it should be familiar to you if you're used to programming in C or you're used to hardware description languages like Verilog or VHDL. We've created an instruction called pushconv, and that's performing both that taking that new value and pushing it onto the FIFO, and then performing the multiply accumulate operation. And again, you can see all of these operations going on here are described in the code. The FIFO is a special hidden register file that's not generally accessible outside of this instruction, because this is the only instruction that uses it, so it doesn't need to be accessed by other instructions. And then we generate the output at the end. And so this is, as you can see here, I mean, this is the IA description. There's a similar CA description, but overall we're doing this in less than 200 lines of code to generate the whole convolution operation. When it comes to the software, so this is now looking at a 3x3 convolution, so a more complex example. This is typically what it would look like in C. As I said, because this is a more complex operation, the compiler couldn't read all of this and go, oh, I've got a magic instruction. But we can quite simply, in some relatively simple inline assembler, we've got our load conv instruction, our push conv instruction that performs that convolution operation. So when we get to the crux of it, as I said, this gives some really, really compelling performance and improvements just by adding these couple of very simple instructions to our existing core. And we can see we're getting a 5x performance improvement, we're getting a 3x power improvement, and yes, there is an area penalty. You do add some logic, you do add some complexity, but overall, if you look at this, you think, well, actually, if you're getting 5 times the performance, another way to look at it would be you can run your processor 5 times slower, and still get the same performance. And that might mean you can run on an older process node, you're not having to use such exotic libraries, and so it can become a virtuous cycle in terms of improvement in that sense. You don't just have to chase higher performance. The power and the area numbers here also come out of our Studio tool, so we have a built-in estimator. So when you're doing your architectural exploration, you can very quickly get estimates for how big a difference it makes in your design choices. So it's not pushing it through to full RTL synthesis, but if you want to quickly iterate, try 3 or 4 different instructions, see what effect they have in terms of complexity, see what effect they have in terms of frequency, you can push that through very quickly and get some of that data out quite quickly. So to conclude, I hope I've shown here how customizing can provide significant acceleration advantages. The benefit of using a high-level language for designing your processor, for customizing your processor, is that it gives you that fast design space exploration. It gives you a very efficient way to customize. And because the Studio tool gives you all of your SDK, it gives you your entire design environment, it gives verification and more. And again, very happy to talk to anybody offline about all of that. But it's a great way to do customized processors for applications like machine learning and neural networks. We're here on the RISC-V stand just around the corner. We have a booth through in Hall 2. If you turn on that corridor and pretty much go straight ahead, you can find us. We've got a demo running with both of these on FPGA. You can see them side by side. You can see the difference. You can see the benefits, and we'd be very happy to talk to any of you more about this. Thank you very much.